Today we will discuss about surface imaging and depth profiling.
So the outline of this topic is firstly we introduce about the basic concept and depth profiling, also the electron microscopy of SEM and SAM.
And after that, we will go through to the SPS imaging and SIMS imaging and depth profiling. And lastly, we will go through Azhar depth profiling and scanning microscopy.
So let's discuss about it. So the meaning of depth profiling is it is a process where element or chemical content of a sample that were measured by a function of depth. Do you know there are many analysis techniques that have been performed by profiling that have been using beam ions such as argon ions, cesium ions, and gallium ions. So other depth profiling techniques are pulses of laser light, plasma beams, glow discharge, and chemical manipulation in the sample of CSE. This depth profile process involves the repeated removal down to the desired depth. Mostly, the surface spectroscopic technique involves probing the surface by exposing it to a flux of particles and simultaneously monitoring the response to this stimulation. For example, to measure the energy distribution of emitted electrons. These techniques can collect information from a relatively large area of sample. There are many variations of this technique, and one of them is localized spectroscopy, which is known as spatial distribution of property. The second one is surface imaging, that is known as surface microscopy. So, both techniques are for spatial localization of the spectroscopic technique. This technique, when we focus the probe, it will interact with only a small region of the surface. If surfaces are bombarded by electrons, secondary electrons are emitted. These electrons carry information on the electronic of the surface. When this localization of the probe into a small area, it gives benefit to call as many as possible outgoing particles, where the detection completes the spectroscopic process to maximize the signal to noise. In order to carry out surface imaging or mapping, the probe must be scanned across the surface, or the surface must be moved under the probe beam. The approach is to allow a large area of the sample to expose to the probe, but only to collect signal from a small region of the sample. In this area, the spatial localization is occurring on the detection side of the technique. It only requires an appropriate lens system to collect as much emissions as possible from the desired part of the surface and focus it onto a detector. To get an image of the surface using a single detector, scan the sample position underneath the detection system. Make use of additional scanning plates in the electron optical focusing system. Other approach is applied a linear array or two-dimensional array of detecting elements. The emission from different parts of the surface is effectively focused onto different parts of the array detector. There are two forms of electron microscopy which provide surface information. The first one is secondary electron microscopy, and the other one is scanning auger microscopy. In SEM, it provides a direct image of the topographical nature of the surface from all the emitted secondary electrons, while in SAM, it provides compositional maps of a surface by forming an image from the auger electrons emitted by a particular element. Both microscopy use the probe beam to obtain localization. So there are other tools about surface analysis, is it?
Yes, it is. It is SPS imaging and SIMS imaging depth profiling. Do you know about it?
No, I don't know.
Okay, let me explain to you. X-ray photoelectron spectroscopy (XPS) is a surface-sensitive quantitative spectroscopic technique that measures the elemental composition at the parts per thousand range, empirical formula, chemical and electronic state of the element that exists within a material. Do you know how much time needed to analyze using XPS? Okay, we need about 1 to 20 minutes to measure all the amount of detectable element, and 1 to 15 minutes for high resolution scan that reveal chemical state difference, and about 1 to 4 hours for measure the depth profile consists of 4 to 5 elements as a function of each depth. The first strategy is the localization by selected limited area analysis. This is the simplest approach to localize the area of sample surface from which photoelectrons are collected from combination of lens and aperture. The achievable spatial resolution is really better than 100 micrometer and can be achieved by two ways. The first way is translating the sample position under the electron energy analyzer so that the analyzed region move across the surface. The second way is incorporating electrostatic deflection plates using the electron optic to move the region from which electrons are collected across sample surface. The second strategy is the localization of the probe by focusing the incident X-ray. This strategy can achieve an axial spot size of better than 10 micrometer and also better resolution. The image may then be obtained either by scanning sample under the focus X-ray beams or scanning the microfocus X-ray beam. The last strategy for spatial resolution is use of array detectors with associated imaging optics. This strategy is to obtain electron energy resolved image at much faster acquisition rate. The spatial resolution achievable using this strategy is higher than other technique, which is better than 5 micrometer resolution.
Okay, now let us proceed to secondary ion mass spectroscopy, SIMS imaging and depth profiling. What is the meaning of SIMS? SIMS is the most sensitive of all commonly employed surface analytical techniques, which is capable of detecting impurity elements that present in a surface layer less than 1 ppm concentration and bulk concentration of impurities around 1 ppb. There are three techniques that involve in SIMS, which is the first one is static SIMS that can be used for sub-monolayer elemental analysis. The second technique is dynamic SIMS that can be used for obtaining compositional information as a function of depth below the surface. And the third technique is imaging SIMS that can be used for spatially resolved elemental analysis. What is the aim of SIMS imaging? Is to obtain compositional image at the surface from secondary ion spectrum with minimum possible damage to the surface. But there is some problem that will occur, which is to ensure that sufficient signal is obtained at desired spatial resolution while minimizing the ion flux incident on any part of surface. But this problem can be overcome by switching from traditional instrumental approach that using continuous flux ion gun and quadruple mass spectrometer detectors to pulse ion source and time of flight TOF mass spectrometers. Why we use TOF mass spectrometer is because it is much more efficient of acquiring spectral data, provide good resolution and sensitivity up to very high mass. Due to this, SIMS image with a spatial resolution better than 50 nanometer will be obtained. What is the aim of SIMS depth profiling is to obtain information on the variation of composition with depth below the initial surface. The main advantage of depth profiling is its sensitivity to very low concentration of elements. There are three factors that make the depth resolution achievable, which is firstly, the uniformity of etching by the incident ion beam. The second factor is absolute depth below the original surface to which etching has already been carried out. And the last factor is the nature of ion beam utilized, such as example, mass and energy of ions. So that's all about SIMS imaging and depth profiling. I hope that you understand.
Azhar spectroscopy is a surface-sensitive spectroscopic technique yielding compositional information. In its basic form, it provides compositional information on a relatively large area of surface using a broad-focus electron beam probe. In this manner, sufficient signal can be readily obtained whilst keeping the incident electron flux low, and thus avoiding potential electron-induced modifications of the surface. As a consequence, the technique is non-destructive when used in this manner. To obtain information about the variation of composition with depth below the surface of the sample, it is necessary to gradually remove material from the surface region being analyzed, while continuing to monitor and record the Azhar spectra. This controlled surface etching of the analyzed region can be accomplished by simultaneously exposing the surface to an ion flux, which leads to sputtering of the surface atoms. For example, suppose there is a buried layer of a different composition several nanometers below the sample surface. As the ion beams etches away the material from the surface, the Azhar signals corresponding to the elements present in this layer will rise and then decrease again. This diagram above shows the variation of the Azhar signal intensity one might expect from such a system for an element that is only present in a buried layer and not in the rest of the solid. In summary, by collecting Azhar spectra as the sample is simultaneously subjected to etching by ion bombardment, it is possible to obtain information on the variation of composition with depth below the surface. This technique is known by the name of Azhar depth profiling. In the early 1980s, two IBM scientists, Pinning and Roher, developed a new technique for studying surface structure, which is scanning probe microscopy (SPM). Here is the branches of SPM, and we going more deeper on scanning tunneling microscopy (STM) and atomic force microscopy (AFM).
Let's take a look at some metal atoms. An STM has two ways to make images at the atomic level. The first method is called constant height mode. A voltage is applied to the needle of the STM. By applying the voltage in connection to an electrical circuit, you create a measurable current. This also causes electrons to tunnel between the particles and the needle when they are close enough to each other. Due to the differentiation of height, the air will act as a neutral barrier for the electron, causing lesser tunneling to happen as the distance between the needle and particles increases. And if the amount of the tunneling electrons decreases, so will the current. With constant current mode, voltage is yet again placed on the needle, causing electrons to tunnel between the particles and the needle. Only this time, the current is kept constant by altering the height of the needle. This is why this method is so time-consuming, because every time the needles needs to be altered exactly to the right height to meet the right current.
Using the detection method, an AFM images the topography of the sample surface by scanning the cantilever over the region of interest. The raised and lowered feature on the sample surface influence the bending of the cantilever measured by position detector. AFM generates an accurate topographic map of the surface by using feedback loop to control the height of the tip above the surface.